So what exactly do we mean by deep learning? Well, the phrase has two different words and they both together connote what we want to mean by deep learning. First, the idea is that it's deep. That means there are several layers of models being stacked upon each other. By stacking, we really mean something like this, where we feed the output of one model as the input to another model. The second part of the phrase is about learning, and it really connotes the use of some type of model that's being composed together in a network. So each of these individual nodes here could be a linear function like a linear regression or a perceptron, but it could be any other type of learning algorithm too, as long as it has the capability to take in multiple inputs, which almost all of them do, as well as generate an output, which all of them do. So any type of supervised classification algorithm can be used for deep learning. Deep learning definitely benefits from scale, so most of the time we use deep learning with neural networks where the neurons or units themselves are just linear units. And so when we compose this in layers upon layers, we get the idea of something that's deep. So you might ask, well, what does deep mean? Well, we saw in the last neural networks lecture, networks that are size 2 or size 3 might be viewed as a neural network. But nowadays, it's very common to have more than 100 layers within a neural network. And of course, this begs the question about overfitting and in particular challenges in addressing the overfitting problem. So there's a very important theoretical advantage of using a deeper representation. We saw that in the last lecture, in our post-lecture notes, that we can approximate any f of x using a universal approximation which uses a finite but possibly very large set of nodes on some interval. What we can see is, without going into the details of the proof in our course, is that f of x can actually be much more compactly represented in a lot of cases by something with a smaller number of neurons where we stack the nodes in the networks together. So instead of requiring something that's exponentially large in size of the number of neurons or nodes, we can use something that's more compact with a larger depth. The larger depth allows us to multiplex and combine the outputs of the previous layer in interesting ways so as to get much more complex and rich models with much fewer representational parameters necessary. So this has the consequence of being very useful from a computational standpoint because we don't need as many elements to calculate, but it also helps us deal with the problem of overfitting because having a lot of parameters in our network by having too many elements will cause poor generalization and overfitting, even though we might be able to approximate the function to any level of fidelity that we want, right? Again, this is the difference between approximation and generalization that we saw in the bias variance lecture. So neural networks have had a long and checkered history, and this is because even at the very beginning of computer science, scientists have been interested in modeling the reasoning capacity of humans. So that was even many decades ago, over half a century ago. But why weren't they popular until recently? There were some really important key problems that prevented the rise of neural networks as deep learning architectures with the huge advances that they've made in many fields in computer science due to a couple of different key points. One was that there was just clearly a very, very large amount of computation that was necessary to compute a neural network. And due to Moore's law's progress, with the doubling of computational capacity every year, or 2 years, we finally achieved enough computational firepower to make neural network calculations feasible within the last decade or so. Secondly, there were problems with the traditional training algorithms that we had for dealing with neural network computation. We learned about backprop in the last lecture, but even that had problems when dealing with certain activation functions that were traditionally used in neural networks, such as the hyperbolic tangent and logistic function. In particular, we'll talk about this problem of the vanishing gradients in the next sections or so. And because of these very difficult problems and challenges, machine learning scientists had gone off in different directions and figured out other important challenges to tackle. In particular, the support vector machine, which is another type of linear unit, which we'll talk about next week, was a very useful model that dominated machine learning performance for many tasks well into the 90s. So that tells you about the challenges. How did these challenges get addressed within the last decade? Well, it was really the perfect storm of several elements coming together, which historically is a very interesting thing. First, the rise of big data was a very important part of this. With the rise of social media, even individual users who were not necessarily tech savvy could be generating data in terms of pictures and in terms of video. All of that raw data created much more data that would be difficult to analyze by hand. So creating features by feature engineering was going to be just too difficult to do. And we needed the capability for machines to generate these nonlinear transformations by themselves in an unsupervised or supervised manner. The second factor we've already alluded to is hardware support. With the rise of gaming, computer graphics had been pioneered and was pushed onto the mainstream. Graphical processing units became widely available with NVIDIA and other chip makers making dedicated computer architectures and chips that were designed to render polygons and other types of graphical units on a much larger scale. Even though central processing units got faster, the ideas of having multiple cores to compute very simple arithmetic operations at scale in a parallel fashion was exactly what was needed to compute neural network parameter tuning. All of these came as an important aspect to deal with memory bandwidth and parallelism that was needed for the types of linear algebra computations as we've been doing in matrix operations that made the training of such algorithms more than a magnitude faster. And finally, there was the invention of particular algorithms and concepts. To take advantage of the large data and hardware support, scientists had to come up with good training algorithms for many layered networks. Proper initialization through pre-training and autoencoding played a big role in creating the capability to initialize well. To deal also with regularization as a second factor was an important aspect to make sure that our stochastic gradient descent and optimization algorithms would actually converge quite well to a generalizable solution, rather than one that approximated well but overfit. And finally, the idea of being able to address specifically the problems with training many layered networks, where the gradient of the error dissipated over time as in vanishing or exploding gradients, was addressed by looking at simpler activation functions such as the rectified linear unit, or more popularly called the ReLU.